I'm going to prove the Pythagorean theorem. Alright, so what does that basically mean? I want to find some relationship, some formula between these two legs and this hypotenuse. Okay? I want to write it out in a numerical algebraic relationship between these two guys. How do I do that? Well, first thing I realize is, well, if I want to find a relationship between these guys, how are they related? Well, they all are sides of the same two-dimensional figure. Okay? They're all sides of the same two-dimensional figure. Now, the question I want to sort of raise here is, what's the relationship between a side and the two-dimensional figure it's a side of? Alright? And I guess specifically, what is its relationship to its area? Okay? So, let's just say I have a square. So this side is the same as that side. What's the relationship between this side and the area? It's x squared. What's the relationship between a side of an isosceles right triangle, where these two guys are the same length? That'll be x squared divided by 2, or 1/2 x squared. What's the relationship when I have a long rectangle like this, where this side is 5 times that side? Well, that'll be 5x squared. What is it like when I have a triangle, a right triangle, an isosceles triangle, where this height here is, let's say, x divided by 3? Then I'll know, oh, okay, the area is x squared is 1 over x squared. So I'm starting to see a pattern here. It's sort of like if I have some shape, any old shape, it can be very strange even, like a pentagon, and I know one of its sides, then I'll know, oh, the area will be some multiple of that side, of the square of that side, okay? Some multiple of the area of that side. And we see that in all of these examples here. This right here, the multiple, the c, is 1. Here it's 1/2. Here it's 5. Here it's 1/6. In general, it's just the area of whatever figure we're looking at will be proportional to the square of its side. That's a very important insight which I'm going to be using here. That'll be central to getting the Pythagorean theorem. The area is proportional. Another way to think of proportional is it's multiple. A multiple to the square of, I'll say, a side. A side. Okay? Okay, and we see that here. Now, how is that useful here? How is that relevant to us? Well, one thing we could do is we could think, well, I have these sides, I want to relate them to this triangle somehow. What if I sort of drew objects on the side here? What if I did something like this, where I made a rectangle on each side, and it was the same rectangle, It was the same rectangle where, this side is like twice of that side, this is twice of that side, this is twice of that side, something like that, okay? Maybe not twice, maybe just some other multiple. And the idea is like, okay, if I have A, B, H right here, then this will be some CA squared, some CH squared, some CB squared. Okay, so I have that, but that's not very useful as it stands, because I have no relationship between these different guys, these different rectangles here and their areas. I want to somehow relate these rectangles to each other. And maybe I think, well, maybe rectangles are the wrong shape to use here. Maybe some kind of triangle, maybe a pentagon, I don't know. So I think, what's a good shape to use here? I could be using these rectangles, could be using some kind of isosceles rectangle coming off of there. Can you use pentagons? What would be a good shape? What's a relevant shape to this problem? Well, here's a relevant shape, this right triangle. Okay, what if I put onto each of these sides a triangle similar to the original triangle, similar to this triangle? All right, let's do that. Let's give that a shot. Okay, so, all right, let's take this and let's draw. Let's see, let me just get that. Let me just make that drawing reasonable here. So let's say it's like this. Okay? So here's phi, here's theta. Alright, let's do the same thing down here. We have theta here. Like that. And phi is right there. Let's do it also on this little triangle here. So here's phi, here's theta. Okay, so that's nice that we've drawn that out, and it's nice that we have the idea, okay, this triangle is a relevant triangle, it's the triangle we care about. What do we do with this? Well, first thing I ask is, and just so we're clear by the way, each of these triangles is similar to this triangle, right? All of them has phi theta, phi theta, phi theta, just like this triangle has, okay? Alright, so what are the areas of these guys? Well, I'm not exactly sure, but I know by this first insight here that they're going to be some kind of multiple of the hypotenuse here, of the square of the hypotenuse for them. So in this situation, the hypotenuse is h, so I'm going to call, so this area is going to be ch squared. This hypotenuse is b, so this is going to be cb squared. This hypotenuse is A, so I'm going to call this one, so this area will be CA squared, okay? They're all similar triangles here, right? This guy, they're all similar triangles, so this C right here, this constant will be the same throughout. The only thing that changes is what's inside of that square, okay? Now by the way, this is starting to feel a little bit similar to the Pythagorean theme here, right? We've got squares of all these guys. Okay, where do we go from here? Well, how is this triangle related to this triangle? Well, let's see. Well, we know it's similar. All of these triangles are similar to this main triangle. What else do we know? Well, we know the length of its hypotenuse. What is the length of its hypotenuse? It is h, which is the length of this one's hypotenuse. So we know it's similar, and its hypotenuse is the same as that one. Oh, it's a congruent triangle. That means it has the same area. So these two guys, they have the same area. Alright? I'll just write some kind of arrow just to indicate that. Alright? So that's great. That's great. This triangle is related to that one in that way. This area is ch squared. Don't quite know what that is yet, but it's nice. What about these guys? How are they related? Okay, let me think about that. I'm going to redraw this triangle down here just to give me a little more space here. So here's phi, here's theta, here's b, here's a. And there's, of course, my other little triangles. Theta, phi. Okay, so how are they related here? Well, let's see here. Well, one thing you sort of see here is that, oh, this thing, if I swung it, if this was a hinge right here, I could have swung this over and seen, oh yeah, this is identical to that. What if I swing these guys over? So if I swung this guy over here, you know, just swung him over where this guy was the hinge, then it's sort of like, oh, they have the same angle, so these two sides will move along the same way. Then I hit the right angle, and I see, okay, and then that cuts up into theta there. All right, and of course this is a right angle right there. Alright, what about this triangle here? Well, let's see here. If this is theta, and this is 90 degrees, and phi is supplemental to theta, then I know this is phi right here. And oh look, this is 90 degrees, and this is a straight line. This is also 90 degrees. this triangle is the same as that one. That seems pretty powerful. As in, these two triangles right here are, well, if you add up their areas, equal this big triangle right here. Alright? And let's see, if these two triangles add up to this, that means their areas add up to that one. And we know the area of this one is CA squared. We know the area of this one is CB squared. So the area of this whole triangle here is CA squared plus CB squared. And the thing is about that is, oh, I also have another way of writing that out. CH squared. And I see, oh, look, you have the C over and over again. I don't need that anymore. I can just write A squared plus B squared equals H squared. Okay, so we got the Pythagorean theorem. Because this triangle is, because these triangles are all similar here, this one, since it's congruent, it shares the same side, we get that it has the same area as the original triangle. And we see here how, oh, these two smaller triangles, smaller triangles similar to the big triangle, they can be fit together so that they are the same here. Alright, now one thing is I want to really nail home this last part, this addition part. Why does that happen? The basic reason is because of a second insight I want to write here. And that's that in any right triangle, is made up of two smaller, similar right triangles. Okay? As in, you will always be, if you have a right triangle here, okay, just any old right triangle that you want. And this side is theta, and this side is its supplement, phi. I'll do it the other way around, just so I'm not so confusing. Then, I can just sort of draw a right angle here that happens to go through, this is at a, this is perpendicular at 90 degrees to the hypotenuse, and it goes straight through this particular vertex here. Then I find, oh, well, if this is 90 degrees and this is theta, this is phi. And since this is 90 degrees and this is phi, this is theta. So I see that, oh, in this big triangle that has an angle phi and theta, I can find two smaller triangles, phi and theta, like that are similar. So this big triangle is made of two similar smaller ones. Alright, now this is where the real key comes in here, is that, alright, I understand, why is it that the Pythagorean theorem, or this formula, let's focus on this original one right here, why is this one the way it is? Why are there squares? Well, the reason why is these three sides, A, B, and H, are related to each other through a two-dimensional figure. And how is the area of that two-dimensional figure related to each of its sides? Well, the area is proportional to a multiple of the squares of a side. So we understand, ah yes, if these three guys, A, B, and H, are going to be related, they have to be related through their triangle and probably through the area. So that's why there's an A squared, a B squared, and H squared. Now, why is there addition here? How did that sneak in? Well, by the second insight, that inside of any triangle, any right triangle, you will find two smaller, similar right triangles inside of there. Okay? So that results in the fact that, all right, these two smaller triangles add up to make the bigger triangle. And that's why the Pythagorean theorem works. That's what you should think about when you think about why is the Pythagorean theorem true. Because these three guys, A, B, and H, are related to a two-dimensional object and its area, presumably. So therefore, the area, if they're related through the area, then that means they're related through their squares, through this first insight. And how are they related specifically through their squares? Through addition. Because any right triangle is made up of two smaller, similar right triangles. So I get this here, and then I can just kill off that C by dividing it out. Okay? So that's how it works. That's how the Pythagorean theorem is demonstrated.